Hello everyone, welcome back to 3 Deviations. In today's video, we are going to do an example with integration by parts to kind of show you how the method functions. So in the last video, we introduced the techniques of integration by starting to talk about integration by parts. We kind of recapped what the formula means, how to derive it from the product rule from differentiation, and also how the Lyautey convention works. That made it fairly straightforward as to how we pick our u and v, or our u and our dv. So in today's video again, I want to give an example as to how this functions before we go diving into some more, honestly, tricky integrals that we'll be dealing with later on in our little integration by parts mini unit. Okay, so before we do our example, let's just recap everything that we did the last time. So we have the formula saying that the integral of u dv minus the integral of u dv is equal to uv minus the integral of v du, right? And so we know that u dv is really equal to, our dv is really equal to a function g of x times dx, right? So let's have a look at our Lyautey convention. So the Lyautey convention. So we start with logarithmic functions, and then we deal with inverse trigonometric functions. So if you remember the logarithmic functions, something like ln x goes to 1 over x when differentiated. So that makes it a lot easier. And same with the inverse trigonometric functions. If I have something like arctan, that goes to 1 over 1 plus x squared. And then we also have our algebraic. And this is where something like x would go to 1. But we also have higher order instances where we would see like x squared going to 2x or something like that. And these are the ones that are perfectly acceptable to pick for our u. Now we also have trigonometric functions. This is something like sine of x going to cosine of x. That doesn't really help us. And then exponential e to the x obviously going to e to the x, or something like 2 to the x becoming even more messy. These are things that we should be choosing for our dv. So after we've gone over that, I think it's a good idea to do our example. So our example is to solve for the integral, the indefinite integral, of x times the cosine of x dx. Now, even though this is an integration by parts unit, I think that we should always look at these integrals as if we could solve them in a more easy fashion. So if there were to be an integration by parts where you could use the substitution rule, go ahead and use the substitution rule. That's going to be easier and it's going to save you a lot of time. But this is looking like something that we can't use the substitution rule for. So we're going to need to use our integration by parts. So first what we need to do is we need to find our u and our dv. So u and dv. So let's say that I picked my u to be cosine of x. My du will be negative sine of x dx. My dv will be x dx, and my v will be 1/2 x squared because we integrate our v. Okay, so now this is, if I were to plug this into the formula, then this is going to become something that looks like, we're going to have v times u, so that's going to be 1/2 x squared cos x minus the integral of 1/2 x squared times sine of x dx. Now this looks like something that this does not look easier to solve than this, so we clearly made a wrong choice. So this is good because now you see what happens when we choose the wrong u and the wrong dv. So now let's choose the right one. So if I have the integral of x times the cosine of x dx, then the right choice is to make u equal to x, because once we differentiate x, then that just becomes 1. And that makes our integrand here a lot easier. So that means that our dv is going to be our cosine of x dx, and then our v is going to be sine of x. Once we integrate cosine of x, then we get sine of x. So now we can plug in. Then we're going to get x times sine of x minus the integral of 1 times sine of x dx. And that constant term again. If this were not a 1, I could also just pull this out using that constant multiple rule, but that is a 1, so we can just get rid of it. that gives us x sine of x minus the integral of sine of x dx. Now, this integral here is something that we can do. So let's do it. We already know that the integral of sine of x is negative cosine of x. So this is going to be equal to x sine of x minus the negative cosine of x. And of course we can simplify, and we also need to add our constant of integration. So that gives us x times sine of x plus cosine of x plus c. And this is our final answer. Thank you very much for watching this video of 3 deviations. In the next video, we're going to be back. We're going to go over how to deal with integration by parts when we're doing it twice. Thank you for watching, and we'll see you in the next one.